6.2 here, what we are trying to study is the normal approximation to binomial distribution. This new section 6.4. So what does that mean? So we are trying to study the binomial distribution. We mentioned that previously, right? If you remember binomial distribution, what does that mean? That means in the experiment you are doing, you will only get two possible outcomes, right? Even if it's not two outcomes, you have to group them into two possible outcomes. Then you can apply the binomial distribution formula, right? So for example, if we know we have given n is equal to 10, p is equal to 30%. For example, based on this information, we can assume the event is like a flip a coin. The probability of getting head is 30% each time, okay? And then you are going to flip the coin 10 times. N is equal to 10, that reminds you is 10 times, right? So in that case here, you have the sample size n, you have a probability p is equal to 30%, right? So what is Q, everybody? If you remember that, PQ always one pair, right? Q is equal to 1 minus P, which will give you 70%. So that's the one we learned previously, right? And then if we try to calculate what's the probability of, out of those 10 tosses, right? What's the probability for me to get a one head, right? If I have to calculate that, I can plug x equal to 1 directly into this formula here. That's the formula we learned in the previous section, binomial distribution, right? So first you choose 1 out of 10. You can consider that way, right? And then you want that one to be a head, right? So that's a p to the first power because it's only 1. And then 1 minus p to the, because you only want 1 to be head. That means the other line tosses should be tail. So 10 minus 1 is equal to 9, right? So probability of head is 30%. So that means probability of tail is 70%. You see that here, right? So 0.7 to the 9th power. Now you multiply them together, you got this probability here is what? 0.121. Follow me, everybody? 0.0121, right? That's x equal to 1. Now, similarly, if we have to calculate out of the 10 tosses, what's the probability for me to get a 0 number of heads, right? That means what? I got all 10 tails, right? So in that case, we got like 0.233. So you see that if I have to calculate any number of heads, right? Probability of getting any number of heads, I can plug into this formula. I can do the calculation, but it will probably take some time. You see that, right? It will probably take some time. Okay, so at the end, I find out all of them, right? So you see that table here, I try to list all the possible value of x, right? Out of the 10 tosses, I can get a 0 number of head. What's the corresponding probability? We find that. What's the probability for me to get 1 head? I have that. 2, also have that. I can calculate each one. It may take some time, right? And then what's very important here is if I plot those number, right? Plot those number together on the XY coordinates, right? So for example, we have like x equal to 3, that's like highest one here. The highest probability, x equal to 3 is like 0.267 like that here, right? And then the other one. Now, after I plot them, I try to connect those data points using a smooth curve, everybody. You see what's happening here? It looks like a bell curve. I mean, not exactly the bell curve, but it looks like that, right? It's getting that, okay? That's the key idea. So in other words, the binomial distribution somehow is related with the normal distribution. We can go further. This binomial distribution is actually very similar to the normal distribution curve. So what does that mean? That means if I have to calculate, everybody, like based on the previous calculation, right? So I have to calculate what's the probability out of the 10 tosses. What's the probability for me to get less than or equal to 3 number of heads? So that means I can get 3 heads plus 2 heads plus 1 heads plus 0 heads. So I can add them all together, right? That's one way. That's one way that I calculate each one, then I add them together. But you can see that here, will take some time, right? Will take some time. So this this curve here, as we see that, right, is not a standard normal distribution curve. It's not. So if you want to say, strictly speaking, it's not a normal distribution curve. However, if we use the 3, which is here, right, the one that we learned already, right? Remember, the normal distribution, everything to the left, if we can convert that one to the z, right, then what we can do is what? We can convert, this is kind of our x, we can convert that one to find out what's the corresponding z, right? Based on z, everything to the left, that is our probability we are looking for. You see that? That's the beauty, that if we can apply the z table, we can find out the probability directly, much faster. Instead of doing this way here, you calculate each one, you plug in, I mean, you have to remember the formula, right? You plug in, you calculate each one, you add them together, compare with the other way. It's much faster here, the other way. Okay, so the idea for this section here is what? We are using the normal distribution to approximate, you see the title here, right? To approximate binomial distribution. That's the key for this section. Everybody, I don't require the calculation part. Okay, I don't require the calculation because that's usually taking some time in terms of calculation. I do require that the basic understanding what we are talking about for this section here. Okay, so that's the one thing I want to point out for this part here. So you can see that as n gets bigger, the curve will be more similar to this normal curve, distribution curve, right? So if we are getting bigger sample size, the curve will be more and more like normal, standard, like those like beautiful normal curve. Okay. Now, another thing I want to mention here is rule of thumb that we can apply this normal approximation to the binomial distribution. We have to satisfy that 2 conditions here. The number of tosses, right, n multiplied by p is greater or equal than 5. So like you multiply those 2 numbers greater or equal than 5, and then n multiplied by q also greater or equal than 5. Then if those 2 conditions satisfied, then it's very good approximation using the normal distribution to do the calculation here. Okay, so in terms of calculation, everybody, I don't require this piece here. If that confuse you, this part here confuse you somehow like that here, right? No worries for that, okay? We can cross that. As long as you know, we can use the normal distribution to approximate the binomial distribution. That's good enough. We don't really want to test you, like how do you convert? How do you do the calculation here? That's more complex. We don't require that. Okay, so the same as those example number 1, example number 2 here, we don't require you to do any of those calculations. You don't see any of those homework questions coming from here. We don't require that. Okay, so as long as you have some very basic understanding what we are trying to do, that's good enough for this section.